Thank you, George, and thanks to Dirk and Michal for organizing, and I'm very happy to be included. Um, this is joint work with my friend Songzi, who's at UCSD. Here is the problem that our paper is attempting to address. You're a seller of a good, and you know the set of bidders who might be interested in purchasing this good, and you know the distribution of the bidders' values. At issue is what the bidders know about their values. So a very standard and classic assumption in mechanism design is that in optimal auction design at least, is that the information that the bidders have about the values can be just summarized by saying each bidder knows their own value. Okay, and it might be that there is some prior distribution over values. So from the fact that you know your own value, you can draw inference about what others' values are. So we could think of there being some signal in the background, and your signal is just equal to your value, and then you can update as a Bayesian from the prior that everyone shares. In this model, we're going to look at more general models of information, where maybe you get less information than your value. Maybe you don't know your value exactly. You get noisy information about it. Maybe you get information about others' values that's more than just learning your own value. Okay, so that could be captured by just a more general model of signals and values, where there is some joint distribution of signals and values, and there is a statistical relationship. There's a prior distribution over signals and values, and then through Bayesian updating, the bidders in the auction can form beliefs about their own value and others' values. In addition, we're going to model a seller who has some uncertainty about what is the right model of bidders' information. Why are we doing that? If I imagine myself trying to sell my condo years hence, okay, I could write down models of information of the bidders who I think might come to try to purchase my condo. But I'll be honest with you, I would not be very confident in any of the signals, in any of the models that I wrote down. I know that there is that bidders are going to have uncertainty about their own values, because of course everybody cares if there's lead in the paint or if there's a crack in the foundation. And there may be complex interdependence between what one bidder knows about those features of the condo and others' willingness to pay for it. So I know that there is really rich information in that problem. I really don't know exactly what model to write down. And I'm a game theorist and who specializes in mechanism design and Bayesian game theory. So, I think it's natural to model a seller who does not know exactly what it is. And if you force me to, I could write down a signal structure, I could write probabilities over them, but I wouldn't really believe it, to be perfectly honest. I don't know how to quantify my uncertainty about the bidder's information with a prior over different models of information. So I want to think about a seller in this situation. And the question is, what auction should this seller run if they have this uncertainty about information that can't be quantified in terms of probabilities? Okay, so obviously in this situation, the standard model of Bayesian mechanism design and optimal auction design isn't going to be helpful, because in that model, you have to write down a specific model of bidders' information in order to be able to solve for optimal mechanisms. And you could say, well, just make a guess. Try to approximate what you think is the right model of information, compute the optimal auction for that. The problem there is, we don't really know how Bayesian optimal auctions are going to perform if the information is misspecified. So in this paper, we're going to go to a real extreme. Rather than assuming that there is a single correct description of the bidder's information, as in the standard model, we're going to basically take a worst case across all models of information, which is obviously also kind of a crazy assumption, because even if you don't know the model of information exactly, you may have some information, or you may know some features of it that would narrow it down a bit. But we're going to look at this opposite extreme, and because that's what we can solve basically. If we knew how to interpolate between the standard model where what the correct information is, and a completely agnostic model where you allow all models of information, we would love to explore that middle ground. but this is basically the technology that we have to solve, is what happens when you allow for all possible models of information. We're going to look for mechanisms that basically maximize minimum revenue of the seller, where the minimum is taken across all models of information and all Bayes-Nash equilibria of the mechanism. Okay, so, because we are so agnostic about the information, these auctions are probably not going to be exactly optimal for a seller who knows some features of the information, but these mechanisms are a benchmark. They're a lower bound on how well the seller can do. If we derive one of these Maxmin mechanisms and it guarantees the seller a certain revenue, and then if the seller is contemplating using another mechanism that can't even achieve that guaranteed revenue, well, then that seller would really have to ask themselves whether they can justify using this other mechanism. Maybe they can for reasons that are outside the model, but not just in terms of expected revenue in common prior information structures and Bayes-Nash equilibria. Okay, I'm going to come back to that in a second. Okay, so here is the main result of the paper. We're going to fix a joint distribution of the bidders' values. You think of that as the input of the problem, the set of bidders and the distribution over the bidders' values. And look at two programs, optimization programs. The first one is the maximum over mechanisms of the minimum over bidder information and equilibria of expected profit. Okay, so this is the seller saying, if I can choose the mechanism, but I'm going to take a worst case over these two, how well can I do? Okay. And the second program is the minimum over information of the maximum over mechanisms and equilibria of expected profit. This is like adversarial nature saying how low can I hold the seller to in terms of profit if the seller gets to pick the mechanism and the equilibrium. A main result of our paper is what we call a strong Minimax Theorem, which says that these two programs have the same value pi star. So why do we call this a Minimax Theorem? Well, because it's like there's a two-player zero-sum game between the seller picking the mechanism, nature picking the information, and we're switching the order in which they move. But it's not a standard, where's the strong part of the Minimax Theorem? The strong part is, equilibrium selection is kind of up in the air. And in this top program, we have the seller taking a worst case over equilibria. And this bottom one, you are taking the best case over equilibria in terms of expected profit. And what our strong Minimax Theorem is saying is that actually the value of these programs is the same regardless of who gets to pick the equilibrium, which is kind of an extraordinary feature in optimal auctions, because usually, we think of the form, which equilibrium gets played. Do you need all equilibria to achieve a favorable outcome, or is it enough that one equilibrium achieves a favorable outcome? We're used to thinking that that makes a big difference in what optimal auctions will look like and the value you can achieve. And here, it doesn't appear to matter. So we sort of started off looking for robustness to information, and kind of get robustness to equilibrium selection for free. So we call the value of these programs pi star. We call that the profit guarantee. And then, in sort of an even bigger result is that you can compute approximate max to min mechanisms and approximate min to max information structures that have profit guarantees that are close to pi star, that have finite action and signal spaces, and you can compute them using linear programs, basically. So these programs are highly nonlinear, but there are particular linear relaxations of them that can be used to compute approximate max to min mechanisms and in min-max information structures, and they have all kinds of structure, which I'll explain more when I get to that part of the talk, if I get to that part of the talk. So how do you use this? Well, this is a pretty abstract theorem, and we've applied it in special cases for the joint distribution of bidders' values. And in those special cases, you can compute max to min mechanisms, and they have structure. And we've described that structure. And basically this, we think the value of this theory is that it's helping us to identify new mechanisms that people have not considered before and may be worthy of study, worthy of further study, may even be of practical value. So one example is Songzi and I have another paper on the case where the bidders have pure common values. And in that paper, we construct an exact pair of a max to min mechanism and a min to max information structure. we basically guessed and verified that solution using these linear programs, okay, using these approximate solutions. We didn't know that the strong minimax theorem was true when we wrote this paper, but we used those linear programs to motivate the solution that we constructed and characterized. And the mechanism has the form of a proportional auction. In a proportional auction, the bidders make bids, which are just non-negative real numbers. The probability you get the good is proportional to your bid, and the amount that you pay is proportional to, well, basically there's a price per unit, which just depends on the sum of the bids. Okay, so there's a relatively low dimensional class of mechanisms that are sufficient to get to this profit guarantee when there are pure common values. And we've looked at other cases. We've looked at the case where you don't know the correlation structure between the bidders' values, but you know each bidder's expected value. Proportional auctions are optimal there too, are Maxmin optimal there too. One example I might come back to if I have time at the end of the talk, which I probably won't, is kind of the opposite extreme from common values. In common values, you know that the difference between the bidders' values is 0, and there's uncertainty about the average value. And we looked at another case where you know exactly what the average value is, but there is uncertainty about the difference between the bidders' values. And in that case, using this technology, we were able to guess and verify what are max-Tuman mechanisms in that environment as well. So the proof is non-constructive. As I said, you know, we sort of look at linear relaxations of these programs indexed by a finite number of actions or signals, and then we show that these relaxations have the same value in the limit. Brief literature review. So there's a mechanism design problem, optimal auction design problem in here, obviously, because, you know, we're optimizing over mechanisms. There's also an information design problem embedded in here because we're taking the worst case over the model of bidders' information. So for that problem, we're building on these papers of Dirk Bergeman and Stephen Morris. And then there's a modest literature on Maxmin auctions that we're building on. And I mentioned the connection to this paper, and this paper is building on earlier work on informationally-robust optimal auction design. Okay, so there's a single unit of a good for sale, and bidders, they have values that are in finite grids, and the prior is denoted mu. A mechanism in this setting is very abstract. It just consists of actions for each of the bidders, an allocation rule that we'll call Q, that says for every profile of actions, what is the likelihood that each bidder gets the good? There's a feasibility constraint, and then the mechanism describes transfers that each bidder makes to the mechanism. And we're going to impose this condition on the mechanisms that we call participation security, which just means that every bidder has a safe word that they can use that says, I don't want to pay anything. They might still get the good, and the good has non-negative values. There's a free disposal assumption, but this the availability of this message means that in any equilibrium, bidder surplus has to be non-negative. Good, and then this is the set of participation secure mechanisms. An information structure is a pair. This is how we're describing the information of the bidders. It's a pair of finite sets of signals for each of the bidders and a joint distribution over all of the bidders' signals and the values, where the marginal on values coincides with the prior. So given a pair of a mechanism and an information structure, then we have a Bayesian game where a strategy for a bidder just maps their signal into a distribution over their actions. There's a set of Bayes-Nash equilibria for that game, and induced profit in the strategy profile is given by this expression here, just the expected sum of the transfers. So here is the strong minimax theorem. Suppose that the prior has full support, technical condition. We don't think it's essential, but it really helps us out in a key step in the proof. Then the inf over these information structures, which have finite signals, soup over finite mechanisms, soup over Bayes-Nash equilibria of expected profit is equal to the soup over mechanisms, inf over information, inf over Bayes-Nash equilibria of expected profit. Okay, so as I said in the introduction, the way we prove this theorem is with a bigger theorem. So to state the bigger theorem, I need to explain to you these linear relaxations that I alluded to or just mentioned in the introduction. And really, these are the main conceptual insight of the paper, actually, is how to form these linear relaxations and then understanding the relationship between the two linear relaxations. So the way they're going to work is they're going to be indexed by a finite number of actions, which is going to be, essentially, so actions are going to be in this grid, xi of k, which are just real numbers between 0 and k in increments of 1 over k, where k is an integer. And M of k are the participation secure mechanisms where the actions are in this space. Really, all that matters is the cardinality right now. And then I of k is the set of information structures where this x of k is the signal space. So we're using x of k for actions up here and for signals down here. A little bit of notation. We're going to use discrete derivatives. Okay, and this is our notation for basically the discrete upward derivative of the ith coordinate with respect to the ith argument. Okay, so we're sort of scaling up by the size of an increment of the difference between the function at x, the ith coordinate of the function at x, and the ith coordinate at xi plus 1 over k. This is the vector of own discrete partials, and this is the analog of a discrete analog of the divergence of a vector field. Okay. Here is the first linear relaxation. And this is a linear relaxation of the max2min program, where the seller is maximizing over mechanisms and the nature gets to minimize over information in equilibria. We're maximizing over Q's and T's. So we're maximizing over mechanisms here. Here's our feasibility restriction on the allocation. And here is the participation security condition. So there is an action 0, and we basically said that 0 means 0. 0 is the participation secure message. And then what's going on up here in the objective? Well, this is maximizing essentially the sum of lower bounds on profit, where this lambda of v is a lower bound on profit for each value profile. And that lower bound is constrained by this last equation. And essentially, the lower bound is related to profit, what x post profit would be at a particular message profile, and what turns out to be a measure of local incentives, the cost of local incentives. That's sort of analogous at a high level to the way local incentives appear in revenue formulas in Myersonian auction design. Okay, so that's what's going on in this linear relaxation. The seller is maximizing a lower bound on revenue across mechanisms, and the fact that we're taking this discrete derivative suggests that it's local incentives. It's the temptation to deviate up to the next higher message that's capturing incentives in this program. So this is program 1. Program 2, okay, now this is a probability distribution over these x of k signal action profiles. And don't worry too much about this formula. It's a discrete analog of an exponential distribution fit to this grid. So it's a censored IID censored geometric distribution with arrival rate 1 over k. Okay, here's the second relaxation. Nature's problem, minimizing over information, max over revenue and equilibria. Here's the information structure. Okay, here's the sigma, the joint distribution over signals and values. Here is the marginal constraint that the distribution over values has to coincide with the known prior. And then these others are new conditions. The second condition, we're going to constrain the seller to use information structures where the distribution of signals is that IID censored geometric. And in these last two lines, what do these say? This W of X is basically the vector of interim expected values of the bidders if you condition on the signal profile. Okay. And then this last piece is basically saying gamma, the nature is trying to minimize the sum of these gammas, and these gammas are essentially upper bounds on virtual values, on Myersonian virtual values. So inside this expression here is the value of allocating the good to bidder I when the signal profile is X, minus some information rent, which depends on local incentives. So this is a generalization of the classic, or generalization special case related to whatever, of the Myersonian formula. So we're used to seeing this guy for a virtual value in Myersonian auction design. When you generalize to interdependent values, as Bulow and Klemperer in 1996 did, then you would get something like this. Where you've replaced the value with the signal of the bidders, but still there is the social value of allocating the good to the bidder minus an information rent. And then there's an extra term, which is the sensitivity of bidder I's value to their signal. Now, if your value is your signal, then this derivative is just 1, which is why it drops out here. But you still get this inverse hazard rate, sort of a measure of the number of higher types who get a rent from mimicking this type. Now we've restricted the seller, restricted nature to choosing distributions that are censored geometric, which basically makes this hazard rate 1. So all we're left with are these two terms in our expression for a virtual value, which is exactly what you see here. So in other words, this linear relaxation is basically nature minimizing the Myersonian upper bound on revenue over all information structures where we've constrained the distribution of signals to be IID censored geometric. Okay, so here's the big theorem. For every K, these linear relaxations that I just described are in fact relaxations. They bound the value of the max to min programs where you have all of the equilibrium constraints. And you can choose any mechanism and information structure. And under this full support hypothesis, in the limit, as K becomes large, these bounding programs have the same value, and that's equal to the pi star. So a fortiori, they're going to squeeze the values of these programs together, and everything coincides in the limit. Moreover, if you have a mechanism that solves the first linear relaxation, then profit is at least the value of that program in every information structure in equilibrium. And if you have an information structure that solves that second program, then profit is at most the value of that program in every information structure in equilibrium. So running pretty short on time, so I'm not going to tell you too much about how the proof goes. Do I want to tell you much at all? What I want to skip ahead to is, okay, so basically what we do in both programs is we normalize to either correlated equilibria when it's nature choosing the information in the equilibrium, or we'll normalize to incentive compatible and individually rational direct mechanisms when it's the seller who's choosing the mechanism in the equilibrium. And then we relax the program further by dropping all of the non-local constraints, either obedience constraints in the case of correlated equilibrium or incentive constraints in the case of direct mechanisms. And we also drop all of the participation constraints except for the lowest type. So that gives us almost the relaxation that we're looking for, except that, and then we take a dual of this inner problem so that it becomes all a soup program or all an inf program, okay? The last thing that we do is we fix multipliers on local obedience constraints or local incentive constraints at a particular value, which is just a further relaxation of these programs. And then we show essentially that those multipliers that we picked are the right ones. The values of the programs with those fixed multipliers coincide in the limit. It turns out that fixing the multipliers in the way that we do, so that the only multipliers that are non-zero are the ones on local constraints, that reduces to an assumption that the distribution of signals is independent, actually. And we pick a constant multiplier, which implies further that the distribution of signals has to be the censored geometric that I introduced previously. So the last thing that I want to talk about, these programs, at the end of the day, we end up with these two programs that I showed you several slides ago. And they were derived in kind of a symmetric way, but from different programs, max over mechanisms, min over information equilibria for this program, and min over information, max over mechanisms and equilibria in this program. And they don't look that closely related right now, but it turns out that they are very closely related in the following way. Over here, you have transfers that appear. It turns out that the transfers can kind of be solved out because all that matters is this difference between the divergence of the transfer and the sum of the transfers. And so we can replace this expression with just a single term that I'm going to call xi. We're going to just call that xi. And if you do that, it turns out that there exists a transfer such that xi is equal to the difference between the divergence and the transfers if and only if this expectation of xi is 0. Okay, so this is an equivalent program to the one I had before. Now, these two programs are almost a dual pair because, look, there's this constraint over here that's saying that the marginal distribution over the value has to be mu of v. Lambda is
Then you have 3 minutes.
Thanks, George. Lambda is the multiplier on that constraint. Here we have the constraint that the marginal distribution over signals is IID censored geometric. Xi is the multiplier on that. We have Q over here. That's the multiplier on this constraint down here on the virtual value. So in fact, these are almost a dual pair with one key difference. If I take the dual of the second program, I get something that looks almost exactly the same, except that over here, local incentive constraints are looking up, and over here they're looking down. And the challenging step in the proof that took us a long time to prove is that in the limit, when the number of actions and signals is large, it doesn't matter whether you measure local incentives going up or local incentives going down, you get the same asymptotic value. Okay, which of course makes sense if you ended up with continuous allocations in the or differentiable allocations in the limit. But it's not obvious that taking limits of solutions in this discrete grid of actions and signals, you would get a continuous solution or differentiable solution limit. But it turns out that it's smooth enough that you can prove that the values of these programs are the same. So just here is an amuse-bouche of how you could apply this to an actual mechanism design problem. Here is this constant sum problem that I was describing it in the introduction, where the value is either 0, 1 or 1, 0. Now, if you solve that max to min relaxation with k equals 50, this is the allocation rule that you'll find. This is the probability that bidder 1 gets the good as a function of the pair of values. So as you increase bidder 1's signal or message, I should say, their allocation goes from 0 up to 1. What is there to notice about this picture? There's a ton of structure. There's a ton of structure. And based on this picture, it's possible to guess and verify what a Maxmin mechanism would look like in the limit. Here is the estimate of the information of the bidders. For most of the signal region, the expected value is 1/2, meaning that the bidders have no information about their values. In fact, we were able to construct mechanisms that analytically solve this problem with 2 bidders. And basically, your allocation only depends on the difference in the messages. When the difference between the actions is large, when bidder 1's action is greater than some threshold above bidder 2's message, they get the good with probability 1. When it's less than x2 minus that threshold, then bidder 2 gets the good with probability 1. And there's linear interpolation in the middle. And you can show that there are transfers that together with this allocation rule will achieve the optimal profit guarantee of 1/2 in the limit. You know, it's not that surprising that the profit guarantee in this problem is 1/2 because there's an agreement theorem that says that, you know, if the bidders had common knowledge of their posterior expectations of the values, then they would have to have the same posterior expectations because of the common prior. So you should be able to have them have a conversation about who has the bigger value, and then they'll agree eventually, and whoever has the higher expected value would be willing to pay 1/2 for the good. So what's interesting about this mechanism is it kind of short circuits that discussion that the bidders would have to make about who has the higher value and what their expectations of the values are. And in every Bayes-Nash equilibriumless mechanism, expected revenue is at least a half, could be more. So I'll wrap up there with some open questions in this agenda. There's a lot left to do, a lot of complementarity with analysis that goes on in algorithmic mechanism design. Here we're focused on robustness to the information, but you could also ask, what if you also wanted robustness to the distribution of values? Can you find mechanisms that provide constant factor approximations when you're also concerned about misspecification of the information as well as the fundamentals? So those are just some of the issues that remain to be explored. Thank you. That was for an earlier talk I gave at Coles. I forgot to change. So let me update that to Dirk and Michal.